In the previous video, we looked at cantilever beams, and now we're going to relate that theory to encastre or built-in beams. We're going to look at two specific cases. We're going to look at an encastre beam when a UDL is applied, and we're going to look at an encastre beam when a point load is applied. So first of all, on the screen here, we have our encastre beam, which is fixed at both ends. And we can see that a uniform distributed load, W, is being applied to the beam. That can be thought of as the weight per metre of the beam. Now, the reason this differs from a simply supported beam is for some of the reasons discussed in the earlier video. What we're going to have at the left-hand support is a turning moment applied here, which is preventing deflection of the beam. In effect, the gradient of the beam at that left-hand support is going to be 0. But likewise, at the right-hand support, we're going to have a turning moment, which is preventing the deflection of the beam. And that turning moment is going to lead to the gradient at the right-hand end of the beam also being 0. So the way that we need to evaluate the maximum bending moments on these beams differs significantly from simply supported beams. However, the process remains very similar. We need to calculate the support reaction at the left-hand support, RL, and we need to calculate the support reaction at the right-hand support, RR. Now, in order to do that, we need to know the total force acting downwards. And because we only have a UDL acting on this beam, we know that that weight is going to be evenly distributed between RL and RR. So let's first of all calculate the weight, and we can add it to our diagram here as capital W. W equals the weight per metre times the length of the beam. Our weight per metre in this case is 225, and the length of our beam is 8.4 metres, giving us an overall weight equal to 1890 newtons. Now at this stage, you could go through the normal method of taking moments about the left-hand support in order to determine the reaction force at the right-hand support. However, from inspection, I can see that that weight must be evenly distributed across the two supports. The weight acts in the centre, therefore RL and RR must be the same, and when added together, RL plus RR must equal 1890. Therefore, RL equals RR, and it's equal to 1890 over 2, which is 945 newtons. Now, our method for producing the shear force diagram is exactly the same. We imagine ourselves stood at the left-hand support, and we're stood at the left-hand support and we're looking left, like so. And we imagine ourselves moving from left to right, and we evaluate each force as we see that force. We have RL causing positive shear, like so. And the value of the shear force at that point is 945. So we're coming up 945 newtons, like so. Now, between the left-hand support and the right-hand support, as I move left to right, I'm going to see more and more of the UDL. But it isn't until I get to the right-hand support, here on our diagram at the top, that I can see all of the UDL, all 8.4 metres. So between the left-hand support and the right-hand support, there's going to be an additional shearing force equal to the weight of the beam. Well, we've already said that that's 1890 newtons. So between the left-hand support and the right-hand support, we're coming down at an angle, and we're coming down by a total distance here of 1890. Well, 945 minus 1890 is minus 945. Now finally, if we imagine ourselves moving just past the right-hand support, so here on our diagram, we can now see RR. RR is also pushing the left-hand side upwards relative to the right-hand side and relative to our position over here. Therefore, RR is also causing positive shear, taking us back to 0 on our shear force diagram. And that's exactly what we would expect. We start at 0 on the left-hand side, and we finish at 0 on the right-hand side. Now here's where things differ. On a simply supported beam, we know that the bending moment at the left-hand support is 0. And we know that because there's no fixture or no support to apply a turning moment. And we know that that's also true for the right-hand support. However, that isn't the case with an Encastre beam. Now for this case, when we only have the weight of the beam or a UDL to consider, we have formulas to calculate ML, the bending moment of the left-hand support, and we use the same formula to calculate MR, the bending moment of the right-hand support. And we also have a formula that we can use to calculate MC, the bending moment at the centre of the beam. And these are standard formulas that are provided on your equation sheet. Now ML and MR are going to have the same magnitude, and the way that we calculate those is as follows. MR equals ML, which equals WL squared, all divided by 12. Now we can plug in values for this. We know that W is 225. We know that L is 8.4. We need to square that and then divide by 12, giving us the bending moment at our two ends equal to 1323 Newton meters. We'll discuss whether those are positive or negative in a moment. Before we do that, let's calculate the bending moment at the centre. Well, the bending moment at the centre is calculated using the formula WL squared over 24. And again, it's just a standard formula that we use for this special case of an Encastre beam that's only being subjected to a UDL. We have 225 times 8.4 squared over 24, giving us a bending moment at the centre equal to 661.5 Newton meters. And as you've probably seen, that's half the value of the bending moment at the right-hand support and the left-hand support. Okay, so if we refer to our diagram, and we refer to M at the left-hand support, and we refer to M at the right-hand support, here and here, we know that they have the same magnitude. But if we consider those in isolation, ML is trying to bend the beam this way, and MR is trying to bend the beam this way. Well, hopefully you can see from that what each of those bending moments is trying to do is cause the beam to hog. They're trying to make the beam take on this shape. Now hogging, we know, is negative. So ML and MR are actually both negative bending moments. They'll be down here on our bending moment diagram with a value of minus 1323 Newton meters. The bending moment at the centre, however, caused by the weight of the beam, is trying to make the beam sag. Sagging is positive bending. So what we end up with at the centre is a positive bending moment, this time of 661.5. So the profile of our bending moment diagram with the UDL is going to appear something like that. Now the important things to take away from this is the magnitude of the maximum shear force. Well, the magnitude of the maximum shear force, referring to our shear force diagram, is going to be 945. Note that the magnitude of 945 and minus 945 is the same. By the magnitude, we mean the actual size rather than the direction. And the magnitude of the maximum bending moment, well, although we have a positive bending moment of 661.5 Newton meters, that isn't our maximum bending moment. Our maximum bending moment, or the magnitude of our maximum bending moment, is going to be 1323 Newton meters. And that's occurring at both the left and right-hand support of the beam. Let's repeat that, and this time, instead of having a UDL, we're going to have a point load, but that point load isn't going to be placed at the centre. Okay, so this time we don't have a UDL acting on the beam. Instead, we have a point load P of magnitude 850 newtons acting a distance of 3.5 metres from the left-hand support. Now, the first thing that we're going to do in this particular example is calculate RL and RR, our support reactions, Now, we need to approach this slightly differently. And the reason we need to approach this differently is because when we have a fixed-in beam, essentially what we have at the two ends of the beam are turning moments, trying to restore the beam back to its original position. Now, any turning moment applied at RR is going to cause an opposing downward force at support RL. And any turning moment at RL is going to cause an opposing force at RR. So essentially, the turning moments at either end of this beam affect the distribution of shear force throughout the beam. Now, for this reason, we have to use some specific equations in order to calculate RL and RR. Now, the first of these equations is as follows. RL, the left-hand support reaction, equals the force 3A plus B times B squared, all divided by L cubed. Now, this is a standard formula, but we need to take a bit of care here because our point load F, given in the equation, is actually P as specified on our diagram. So P and F here are interchangeable. The other thing we need to establish is what A and B are in this particular equation. Well, sometimes we'll see these labelled as the left-hand support being A and the right-hand support being B. In which case we might see this labelled as RA instead of RL. Well, small a is the distance from the left-hand support to the application of the point load, this distance here, A. And B is the distance from the right-hand support to the application of the point load, here. So as we can see, A in this equation is 3.5 metres, and B can be easily calculated because it's the length of the beam, 8.4, minus A, which is 3.5, giving us a length B equal to 4.9 metres. So now, applying this equation, we can calculate the magnitude of our left-hand support, RL, or often referred to as RA, depending on the diagram and how the supports are specified. Let's stick with what we have. We have RL equals the force, which is interchangeable with P, 850, 3 times A, so 3 times 3.5, plus B, 4.9, times B squared, or 4.9 squared, all divided by the total length cubed, or in this case, 8.4 cubed. Now, running that through the calculator gives us a left-hand support reaction, RL, equal to 530.27 to 2 decimal places. So 530.27 newtons. Now, when we rewrite this for our right-hand support, we need to ensure that we substitute A's for B's to ensure we're accurately calculating the support reaction. Now, these two equations for RL and RR, or interchangeably RA and RB, can be found on the equations and information sheet. But let's work this for RR. We have F. This time we have A plus 3B times A squared over L cubed. And running our numbers, we have 850. A is 3.5 plus 3 times B, or 3 times 4.9, all multiplied by A squared, or 3.5 squared, and all divided by our length cubed, 8.4 cubed. Now once again, let's run that through the calculator, and this time we get a right-hand support reaction equal to 319.73 newtons, accurate to 2 decimal places. Okay, now at this stage we can do a quick check because we know that the sum of the forces acting downwards must equal the sum of the forces acting upwards. So if we add our RL and RR values together, as we would expect, we get a sum of 850 newtons, because that's the sum of the forces acting downwards. So just to repeat, we can check these values, because adding RL to RR gives us the forces acting upwards, and that's going to be balanced by our forces acting downwards of 850 newtons. Okay, the next step then is to complete our shear force diagram. Now, moving from left to right, we have RL acting upwards, or causing positive shear of 530.27 newtons. So we're going up, 530.27. Our shear force remains constant until we get to the point of application of force P, and force P pushes down 850 newtons. So we have minus 850. Well, 530.27 minus 850 gives us minus 319.73. We continue to move from left to right until we reach the point of application of RR, and RR also causes positive shear of 319.73, which restores us back to the zero line on our shear force diagram. Okay, so next we're going to determine the maximum bending moment acting on our beam here. So the way that we're going to determine the maximum bending moment is first to determine the bending moment at the left support, the bending moment at the right support, and the bending moment at the point of application of the force. The larger of those three bending moments will be the maximum bending moment acting on this beam. So let's clear some space and look at the equations used to calculate ML, MP and MR. So to determine the moment at the left-hand support, we use the formula P B squared A over L squared. And to find the moment at the right-hand support, we use the formula P B A squared over L squared. So what's A and B? Well, on our diagram, A is the distance between the left-hand support and the point load, so this distance here. And B is the distance between the point load and the right-hand support here. So we know that A is 3.5 metres and B is just 8.4 minus 3.5, which is 4.9 metres. So it's simply a case of plugging in our numbers. We have, for the left-hand support, 850 times B squared, which is 4.9 squared, times A, which is 3.5, all divided by the length squared, which is 8.4 squared. And that gives us a bending moment equal to 1012.3 Newton meters. Now we can do the same for MR. We just use the standard formula. We have P, which is 850, times B, which we've said is 4.9. This time it's times A squared, so times 3.5 squared, divided by L squared, which is 8.4 squared. And this time we get a bending moment equal to 723.1 to 1 decimal place. We'll look at whether they're positive or negative in a moment. Before we do that, let's calculate the bending moment at point P. Now, once again, we have a standard formula. And the formula for this is 2p a squared b squared over L cubed. These are all provided on the formula sheet. So we have 2 times 850 times 3.5 squared times 4.9 squared divided by 8.4 cubed, which equals 843.6 Newton meters. Now once again, if we refer to our diagram, we can see that the moment at the left-hand support is resisting the sagging effect caused by P. So it's causing a moment in this direction. And we can see the same is true at the right-hand support. P is trying to cause the beam to sag, and RR is trying to restore that or counteract that, like so. Therefore, at the left-hand support, we have a negative bending moment. At the right-hand support, we have a negative bending moment. And because P is trying to cause the beam to sag, P is causing a positive bending moment. And we end up with a bending moment diagram that looks something like this. Now, if we include some values on here, we know that ML is minus 1012.3. And we know that MR is minus 723.1. Both of those are in Newton meters. And we know that the bending moment at the point of application of the force, MP, is positive 843.6. So finally, we can consider the magnitude of the maximum shear force by referring to our shear force diagram. We can also determine the magnitude of the maximum bending moment. Now the highest magnitude there is 1012.3. And in actual fact, when we have Encastre beams, the maximum bending moment will always occur at one of the supports.